Well, good afternoon. It's 5:36 on the 7th of June. This is a Wednesday evening, 2017. We're supposed to be Physics 2, and right now I'm the only person in the room. This is a little disconcerting because we're supposed to have class, so I'm going to continue with class. Hopefully there will be some people coming in. There were 2 people here for the first class that usually come to this class too. They left. I thought were coming back, and I haven't seen them yet. And then there's several others that I was expecting to be here. So I know Sam won't be here because he did call. That's one reason it's 5:36, and I haven't started yet is because I got the phone call from him, and he had to go to the emergency room this morning in a fair amount of pain. He's still in some pain, but they gave him medicine for pain, so he shouldn't be driving. So he won't be here today, I know. But I don't know where everybody else is. So anyway, let's get going. We'll start the slideshow from where we are. This is where it was indicated that we left off last time. Let me say just a couple more things before I get going today on this. First, I think I told you last time, boy, there's so many changes here, I don't know. Told you last time they had decided I would get paid for an overload, but that meant I had to extend my office hours because if I teach an overload, that means I'm supposed to be here beyond my 40 hours a week. So I had to change my syllabus and change my locator card and all that kind of stuff to account for that. Well, as it's turned out, I did that. In fact, that's what took me most of yesterday morning, and I think I got it all done in the morning, but I didn't get much time to do as much grading as I wanted to do because I was trying to get all that done so I could get Blackboard updated. I got it updated. Everything is as it's supposed to be now. And then I found out today that the meeting, I think I told you all of this earlier in the term, but if I didn't, I'll tell you now. Sometime late last term in spring, I got an email from the National Science Foundation saying that they would like for a team from our college to go to participate in a meeting that they were holding, and they gave us 3 places and days and times. Well, I forwarded this on to the powers that be that make the decisions on this and said, that sounds good, I'd like to go, especially if I could go to the meeting that's in Spelman College in Atlanta. That's close. It's on a Friday and Saturday. That wouldn't interfere with classes. I'd like to go if we can do that. Well, after I got within a day or 2, I got a phone message from the Vice President's secretary that he wanted to talk with me, but he wasn't available then, so we went back and forth on phone tag for a while. Finally, when we talked, he was going to request, he's going to be part of that, okay, because that's part of his job, but he didn't want to do the Spelman at Friday and Saturday. He wanted to do Xavier College down in New Orleans on a Monday and Tuesday. I said, well, I've got classes Monday and Tuesday, lots of classes Monday and Tuesday. He said, well, I didn't want to mess up a weekend. So you see right there one of the differences between instructors and administrators. I'm concerned about classes. They're concerned about messing up a weekend. So it looks like coming up later this month, not this coming Monday, but the following Monday, I think it is. I'll get the date exactly later. We're going to be going to Xavier. Now, I'll be there Monday and Tuesday, meaning we won't have class. Now, I'll let you know exactly the date and situation. However, I found out this since then, okay? And this is that Dr. DeLucas, with whom we have a grant, a NASA grant, is wanting to do a couple of lectures, and he specializes in optics and I think labs associated with it. We do have an optics chapter coming up later, so what I'm thinking of doing is if I can schedule him to teach the Monday I'm going to be gone, then he'll do the optics that day and maybe do a lab with it, and then we won't lose a class, and that means we won't have to make up a class. and we'll just change the order. Okay? So the jury's still out on that. We'll find out if we can work it out. We're going to do that. Okay? That's one thing. Another thing, let's see. Okay, I think that's about all of it. But that means tomorrow I've got to be doing all my travel work for the that meeting coming up. Hopefully that won't take too long, but that's why I wasn't able to finish grading. I got at least 3 of the labs graded, and that left 3 that I haven't graded yet. But I don't have the grades in Blackboard yet because I just ran out of time, mostly because I had to do all the changes to my syllabi and locator card and get all those loaded into the all my classes. That's 6 classes, so it took a while to do that yesterday. Now, here's the other thing. I knew there was one more thing. Since then, also I found out they didn't put in my request for an overload contract. So I'm not sure if I'm doing an overload or not. I think I will be, but the other department chair thought I was going to do it. I said, but I can only do it for math. I can't do it for natural science. She said, oh yeah, that's right. You got it. So since my overload is the physics and physical science combined, then that should be under that. So she said she would get it done or get it corrected or something. I don't know. I do not know, so we'll just have to see. All right, enough of that. Let's move on with electrical field lines. This is on page 507. That's where we left off last time. Okay. And again, you'll see the name Michael Faraday come up. He's the one who introduced this concept, and we'll see that in a second. So here we go. Electrical field lines are a convenient aid for visualizing electric field patterns, and this is to draw these lines pointing in the direction of the vector field, the field vector, at every point. Okay? And that's what these field lines do. They basically connect all the points together, showing the direction of the electric field. Now, they are an artificial construct. You can't draw them all because they're infinitely close, infinitely far. I mean, they're just all over the place. You just draw some to represent them. And mostly what we draw is 2 dimensions, and of course the field lines go in 3 dimensions. But these lines are called electric field lines. They were introduced by Michael Faraday, whom we talked about last time. They're there. Now, there is a tip that's listed here, and let's see if it's in the slide set. Well, let's hit this too. The field lines are related to the field in the following manners. The electric field vector, E, is tangent to the electric field lines at each point. So the field vector and the field lines aren't quite the same. The field vector, E, is the tangent line at every point on the field lines. The number of lines per unit area through a surface perpendicular to the lines is proportional to the strength of the electric field in a given region. Okay? That's number 2. These are the 2 things listed on page 507 at the bottom of that page. Let's see if they get the tip in there. I don't think so. Okay, so I'll read the tip to you. Electric field lines aren't paths of particles. Electric field lines are not material objects. They are used only as a pictorial representation of the electric field at various locations. Except in special cases, they do not represent the path of a charged particle released in an electric field. Okay? They may, but that's not a guarantee. All right. Top of page 508. Electric field line patterns. Okay? Electric field lines, the construct that we use for that, they emanate from a point charge or go toward a point charge. Okay? The lines radiate, if you have a point charge, the lines radiate equally in all directions. Now this shows 2-dimensional. There's become something coming out at you, out of the page, going at angles from the page, going into the page. They're all over the place, okay? But the lines radiate equally in all directions, not just two-dimensionally, but three-dimensionally. For a positive source charge, the lines will radiate outward. In other words, the arrows are pointing away from the positive charge. So for a positive charge, the lines radiate outward. On the other hand, for a negative source charge, the lines point inward, okay, toward the negative point charge. And we talked about this before, that the fields do this, the field lines do this. For a negative point charge, the lines converge inwardly, okay? Now, a few rules for drawing these electric field lines. The lines for a group of charges must begin on positive charges and end on negative charges. If you don't have a negative charge on the page, they go to infinity, okay? If you have positive and negative charges, they start at the positive charges, point toward the negative. In case of excess of charge, some field lines will begin or end infinitely far away, and that's what I was saying. If you say don't have either a positive or a negative, then they either go toward or come from infinity, or if you have excess, some of those will, not all of them. The number of lines drawn leaving a positive charge or ending on a negative charge is proportional to the magnitude of the charge, okay? And this one other very important point, no two field lines can ever cross one another. Ever. Okay? Now, let's see some examples of this. All right? Kind of a new definition for you here. An electric dipole. That consists of two equal but opposite charges. So this one that's pictured here shows a plus charge and a minus charge. Since this is a dipole, the magnitude of the charge is the same on each of those. The signs are just opposite. With the magnitude being the same number of field lines leaving the positive charge must equal the number going into the negative charge. Okay? Now, we don't have an excess charge here, but because field lines emanate and go in all directions and come from all directions, you can't link all these, so some of these are acting like they are going to infinity. In fact, I could easily see, I think I'll go to a different color here, see if I can get this to match, okay? Won't match exactly. But this field line could come on over and connect with that one, okay? This one could come on around here and connect with this one. This one could come on around here and connect with that one. But at some point you run out of space, okay? And so you can't draw them all, okay? Same thing here. This one could connect with this one. This one could connect here, but again, you run out of space, yuck. And you can't draw them all. Some of these, like this one, looks like it heads toward infinity and never comes around. This one seems like it comes from infinity and never goes around. And maybe some of those others too, okay? You just can't draw them all, okay? There's an infinite number of them to boot, okay? So electric dipole consists of two equal or opposite charges with a high density of lines between the charges, indicates the strong electric field in this region, okay? That indicates a very strong field immediately in between those two charges. Number of field lines leaving the positive charge equals the number terminating on the negative charge because they're exactly the same magnitude. Thank you for coming back. You're the only one so far. Hopefully others will be coming.
We're in a group meeting.
What's that?
And we're in like a group message thing.
Right.
With all of us. And I can tell you which ones are not coming.
I know Sam's not coming. He called me.
Okay, so Tia, her first name is Tia.
Tia, yeah,
She's coming.
good.
Brianna Walker said she's still in Huntsville for work. I don't know if she's coming. So, Megan Collins,
Right.
she's not coming.
Oh, she's not?
She's sick.
Oh,
She
yeah.
won't be able to make it.
Okay.
So,
How about FA?
FA. She's coming back. She
Okay,
went to
good.
get something to eat this morning.
Okay. So you said FA was, Tia was, Megan's not.
Brianna, I don't know. She said that she was in Huntsville for work and she didn't know they were going to keep her this week.
Right.
So I don't know.
How about Courtney? Is she on yours?
Let's see.
I know Sam's not.
Oh, okay, well, never mind. She said, hey, I'm not coming to class. I'm sick, so if anything important happens, please let me know for us to try and do the test tonight.
Okay. And you said Brianna's in Huntsville, so the odds are she's not coming. Okay. Then let me get set up for people being here. When no one's here, I don't put on the projector because you can see it. What the lights so you can see better.
Are we going to do lab since it's not many people?
If we finish the chapter, possibly. I don't know. Since we're all sort of to a slow start here, I've been picked up and went, but you know it's. I'll restate this again because I'm not sure you'll go back and listen because you only missed a few minutes. I can't remember if I told you early in the term because you're in 3 classes. You probably heard it sometime. There is a meeting that I was afraid would be scheduled for a Monday, Tuesday. I had requested if I was going to participate to have it on a different location on a Thursday, Friday, a Friday, Saturday, so I wouldn't miss any classes. The vice president decided not to request that time, to request Monday, Tuesday, because he doesn't care about missing classes. He didn't want to miss a weekend. Shows the difference between instructors and administrators. Okay, so now we found out it is on for Xavier University or college or whatever it is down in New Orleans. So we got further to go, fly rather than drive, cost us more, and we missed classes. What a deal. Okay, but you may not miss any classes because I just remember when I went out to get the lab run off for the leather course and stopped to see if the lab room was available. What I found out then also is that Dr. DeLucas, who we're on a grant with, a NASA grant, he specializes in optics and possibly vibration and waves. I don't know about the first one, but the thing is this class has a chapter on optics coming up. So if I can get him to come do his optics lecture the day I'm going to be out of town, then that will kill 2 birds with 1 stone kind of. Gives him a chance to do it, but that means we don't have to make up the class. So I'll see if we can work that out. I just heard that he was wanting to do it this summer. I didn't know if he was going to do any in the summer or not, but he says he wants to. So if we can work it out so he can, then that's what we'll do. And y'all won't miss a class. I won't be here, but he will be. Okay. I don't know if it'll work, but we'll try. All right. And also, I did get, this is so incredibly crazy. You know, they told me last week they would pay me for an overload. So that meant I had to extend my office hours because if you're working overload, you're supposed to be here longer. So that meant I had to change my syllabus for every course I taught and the locator card and get that corrected on every course. I teach 6 courses. So yesterday morning, I took almost my full first hour of office time dealing with making all those changes. Okay? Got them all done. And then that same visit that I made there, the person I was talking with, I said, by the way, did you get Dr. Bryant's physics classes in? She said, contract request. She said, yeah, I think I did. I said, well, did you get my overload done? Oh, no, I don't do the overload for you. I said, well, it's physics. I only do math. I can't do physical science. I mean, the natural sciences unless you want me to. Oh, no. Yeah, I have to do that. So I don't know. It hasn't been done. I hope it will be. Otherwise, I got to change everything back again. But that's neither here nor there. It's somewhere. I don't know where though. Okay. I think that was most of what I was saying at the beginning. All right. Here's where we were. I just talked about a few slides before this and this one. This is an example of an electric dipole. Electric dipole are two equal but opposite charges, meaning the magnitude of charge is exactly the same, but the sign is exactly different. 1 plus 1 minus. Remember about field lines? They always leave from a positive charge and go toward a negative charge. And if the charges have the same magnitude, which a dipole are required to be, then the same number of lines leaving the positive charge must be going toward the negative charge. Of course, you can't draw them all because there's a different number, but you draw an equal representation. The proportionality must be the same. Now, I said before, and I drew them in here, you can't draw them all, but usually you run out of space, and this doesn't look like it's ever going to get to either one. So some of them may not connect, but all that do connect, they must leave one and converge on the other. Okay. And here is Tia, right?
Yes.
Yes.
And, you talked about
About what? Oh, okay. All right. Okay. And I think I said this too, but let me go and say it now because I forgot. I didn't quite finish grading all of your labs. I got 3 graded. I had 3 left to go. But because I was tied up doing all the administrative stuff yesterday, plus my first class, which has 20-some people in it, I had all those labs to grade too. So I got those graded, but I don't have any of the grades in Blackboard yet. Hopefully tomorrow I can do that. Tomorrow I've got to work out my travel for the trip coming up later this month. And I was telling Shakina about that too. If I pronounced you right. Yeah. On a Monday later this month, I've got a meeting down in New Orleans. I think I told you all about that early in the term. I had requested we go to the meeting in Atlanta, which is much closer, on a Friday, Saturday, so it wouldn't interfere with classes. The vice president overrode that. And he didn't want to mess up a weekend. He didn't care about messing up classes. Great. Okay. But I'm trying to work it out so that Dr. DeLucas, who we are on with a NASA grant, who wants to do a lecture or so on optics, that we'll just move up the optics lecture to the Monday I'm gone, if I can schedule it with him to do so. Now, he may be waiting for the equipment to come in to do the lab, but it would be better just to get something done rather than nothing. So I'll try to work that out. Okay, so let's get back. So this is an electric dipole. This is illustrating electric field lines, the patterns of that. That electric dipole consists of 2 equal in magnitude but opposite in sign charges. Notice here, because normally these field lines would radiate outward evenly, and these would too, inward evenly. But when they're close to each other like this, some of the field lines bend down and congregate in between. Okay? Spread out a little back here and concentrate here. Okay? In so doing, you see you have a very strong field here because the density of the high density of the lines between the charges indicates a strong electric field in that region. Much weaker here and here and here, here. Very weak out there, very strong in between. Electric dipole. What if you have, and this is figure 1515, bottom of page 508, what if you have either two positive or two negative charges, two equal but like sign point charges, okay? Now if they're equal in sign, then when you represent them, make sure you have the same number of field lines coming out of this one as that. Because what you do, if this was half the size of this one, you have half the field lines. If it was twice, you have twice the field lines. 1.5 you have. So you have to do that, so make sure you have them all. But these are like charges, so they're repelling each other. So the field lines are going toward, but then moving away from one another, because field lines can never cross. They can connect if they're opposite charges, but if they're same charges, they cannot. So these that are, again, in the center here, they look like they're emanating random, equally around, but then when they see the others, they move away from each other. And this is why you have repulsion in like charges. So actually, you have more of a concentration on the backside and no field lines in between, because they bend away, right? So at a great distance from the charges, so if you got way out here, and these are really close together here, you got way out here, then your field distribution looks like it's a single charge, single two positive charge. Because all the field lines then, by the time you get way out there, again, are evenly distributed around that center. Okay? So at great distances from the charges, the field would be approximately that of a single charge located at C there of 2Q, positive 2Q. The bulging out of the field lines between the charges indicates repulsion, so you think of them as sort of leaf springs. They bulge out and then push each other away because they can't ever cross each other. Okay? That's the repulsion. The low field lines between the charges indicates a very weak field anywhere in the region C. Okay? Now, looks like there's some questions that go along with this. Yeah. Your quick quiz 15.6 on page 509, top of that page, refers to this figure on the bottom of page 508 on the previous page. Okay. Rank the magnitudes of the electric field at points A, B, and C in figure 15.15, this one right here, with the largest magnitude first. Which of these positions, A, B, and C, has the largest magnitude of field? That's related to the density of the field lines around it. So that has the smallest. There's no field lines right around here. Whereas A, you got 2 here. If you extend a little further, you got 4. But you see, these are closer. So A is the largest field, B is the second, C the third. So it would be A, B, C. Okay? And that should be answer A. Let's see how they do in the back. This is topic 15.6. A, sure enough, they're right. All right. Now, there is another figure. Let's see if they show that one. Yeah, this one. Electric field line patterns. If you have unequal charges, like this one, the positive charge has plus 2Q, the minus charge has minus Q. So, you've got to have twice as many field lines emanating from the plus 2Q as you have going to the minus Q. Okay? So since they're unequal charges, you have unequal field lines. So this shows 1, 2, 3, 4, 5, 6, 7, 8 that connect, and additional 1, 2, 3, 4, 5, 6, 7, 8 that don't connect. So you must have as many, you must have basically 16 field lines here for every 8 here, because this has twice the charge. Now, field lines are just a construct, so whatever you choose as your baseline, you have to make sure you get the ratios right. Okay? So note that two lines leave the plus 2 charge for every line that terminates on the minus Q. A great distance from the charges, if you were way out there again, this would look like a single charge of plus 1 Q. And you see 1, 2, 3, 4, 5, 6, 7, 8. That would indicate plus 1. You get far enough out there, and that almost is symmetric. Okay? It makes it look like. But again, your strongest field is in here. Okay? I didn't quite draw these evenly, but the strongest field would be in the field. 2 field lines leave plus Q for every one that terminates on minus Q. Does that make sense? Now, there was a little part of me that was wondering if I ought to draw these every other line goes to minus Q and the others go to, don't. But you can't do that, because if you had another line here, it has no choice but to go to here, because it has nowhere else to go. Field lines cannot cross each other. Okay? So therefore, if you put another one here, you'd have to have another one out here that doesn't terminate on Q or minus Q. Okay. Any questions on that? Okay. The last slide on electric field lines. Electric field lines are not material objects. This was the tip that I mentioned on the previous page. They are used only as a pictorial representation of electric fields at various locations. They don't really exist. They are modeled for us to indicate what's there. They generally do not represent the path of charged particles released in the electric field. That is separate from the field line. The field lines are a representation. The path may be a little bit different. Okay? You'll find that same information in your text as tip 15.1 on page 507. I didn't know it was going to show up as a slide here, so I mentioned it already. Okay. There is an Applying Physics 15.1 measuring the atmospheric electric fields. It's mostly conceptual. Okay, there's not a lot there to actually calculate, but it's a pretty good thing to read. I would definitely take a look at it. We're moving now to 15.5. Now on the slide it says 15.6 because one of the early sections in the new text was a 15.1 and 15.1.2, whereas in the old it was 15.1 and 15.2. So they got the numbering ahead. But this is the same thing. Conductors in electrostatic equilibrium. Okay. What's the difference then? When no net motion of charge occurs within a conductor, the conductor is said to be in electrostatic equilibrium. Okay? Electrostatic, this means charge, electrons, static, stationary. Equilibrium, everything's balanced. If everything's balanced, everything's still, you're in electrostatic equilibrium. No net motion of charge within the conductor. Now, is that saying there's no motion? No, there's always motion. Always motion of charges. But there's no net motion. For every charge you have going one way, you have a charge going another if there's no net motion. There's random motion always. But if that random motion always balances out then it's said to be in electrostatic equilibrium. Now, an isolated conductor has the following properties. This is a conductor sitting out here, not attached to anything else. Okay? The electric field is zero everywhere inside the conducting material. What do you want that material to be? A wire? That's a good conductor, right? Okay, if it's a wire, all the charges that you have are on the surface, nothing in the interior. What if it's a sphere, a conducting sphere? All the charges on the outside, nothing on the interior. No excess charge. Okay? I'm sorry. Wait. Let me back up and say it the way they did. The electric field is zero everywhere inside the conducting material. Okay, I've saved charges. Field is zero. Okay? In a wire, on a sphere, on a block, whatever you got. Okay? Any excess charge on the isolated conductor resides entirely on the surface. Okay, that's what I was saying before. Excess charge. Sure, there's charges, but they're not excess. They're all balanced on the interior. That's why the field is zero. On the exterior, if you have excess charge, they always go to the outside, the exterior. Okay, this is a conductor now. Continuing, the electric field just outside the charged conductor is perpendicular to the conductor's surface. So let's say it's a wire, a long straight wire. Then the electric field would be pointing out or into the wire, depending on what charge is there. Positive pointing outward, but always perpendicular to the surface. If it's a sphere, radially outward or radially inward, just like the points we were seeing before. A box, inward here, inward here, or outward here. They're always perpendicular to the surface. Okay? On an irregular shaped conductor, let's say it's a blob. Okay? No specified shape. Okay? I don't see any exact blobs here. Let's just imagine this is a blob. It's irregular shape here. Okay? The charge accumulates on locations where the radius of curvature on the surface is smallest, that is, at sharp points. Now, in reality, the charges are always on the surface and fairly evenly distributed on the surface, but because you have surfaces closer to each other here, you have the charge tends to accumulate here. Here, where it's fairly flat, they distribute more widely, okay? So any place where you have a small curvature, that's where they accumulate. Now, did I give you the illustration before when we were doing electrostatics of walking across with rubber-soled shoes, say, or leather shoes on cheap polyester carpet in a motel or something? You reach out to open the door, metal door and metal frame, and you get a shock? Didn't mention that. Okay. That has happened to me. We used to do radon research down in Florida and have to spend our research dollars making trips down there, doing measurements, doing field work and stuff like this. Because we want to spend more on research, we stayed as cheap places as we could get by with that were close. And it never failed that some of those places had cheap polyester carpet, you walk across that with either rubber-soled or leather-soled shoes, and you would build up static charge. You reach for the doorknob, and if that building was made not of wood, but of metal construction, it was well-grounded, you got shot. You never experienced something like that. Sliding across the car seat, reaching for the handle, and get a little bit of a shock. Okay, same type of thing. Okay? Now, how can you avoid feeling the shock? This was what I learned to do. Hold the key here. I built up charges on me, so the charges are going to accumulate at the places of smallest radius of curvature. That key has a point. Very small radius of curvature. So hold that next to the door, and if it's dark, sometimes you can hear it, sometimes you can see it. you see the spark jump, but it doesn't shock me because it's between the key and the door. I'm not part of it. If I reach out, it's between me and the door, and I feel it. Okay? It's not bad, but it just surprises me. So, same thing, sliding across the car seat. Every time you do it, you get a shock. Just take your key and touch that to the handle. You'll see or hear the spark go there, and then you discharge yourself, and then you can get off. So the on irregularly shaped conductor, the charge accumulates at locations with a radius curve here as well. That is the sharp points. Keys make great sharp points, and they're metal, so they're good conductors. Okay. Here's property 1. Okay? These are the properties listed at the top of page 510. The electric field is 0 everywhere inside the conducting material. We just said that, right? Consider if this were not true. If there were an electric field inside the conductor, the free charge would then move and there would be a flow of charge. But our assumption here is that you're in an electrostatic condition that you don't have a flow of charge. So therefore it must be that the field is 0 on the inside. If there were movement of charge, the conductor would not be in equilibrium. You would not be in electrostatic equilibrium. You would be in electrodynamic. Maybe not even equilibrium. Okay? Property 2. An excess charge on an isolated conductor resides entirely on its surface. That's the charge. The other was the field. Well, it goes hand in glove. If the field is 0 there, that means there's no excess charge there. If there's excess charge, there'd be field. So therefore, the excess charge can't be on the interior. It must be on the surface. So any excess charge on an isolated conductor, isolated now, not connected with anything else, electrostatic equilibrium, okay, that resides entirely on the surface. This is a result of the 1 over r squared repulsion between like charges in Coulomb's law. Because if you have a conductor, those charges, excess charges, whether they be positive or negative, they try to get just as far away from each other as they can because they're repelling each other, right? Now, if you have balanced charges, they're affecting each other. That's not excess charge. Excess charge would either be all pluses or minuses. So to get as far away from each other, where would that be? It would be on the surface. If some excess charge could be placed inside the conductor, the repulsive forces would push them right back out again as far apart as possible, causing them to migrate to the surface. So therefore, property 2, the excess charge would be entirely on the surface. Make sense? Property 3, an electric field just outside a charged conductor is perpendicular to the conductor's surface. Okay? It sure doesn't look like it in that picture, does it? Consider what would happen if this were not true. So let's say that field is at an angle, not perpendicular. Okay? The component along the surface would charge. If the field is like this, now this is supposed to be equal electrostatic equilibrium. Everything's at rest, nothing's moving. So if you had negative charges here, the field is like this, that has a component in this direction and a component in that direction. Well, the negative charges, because they would move in the opposite way that the field line would be doing, then they would be moving in this direction. There would be a force here. If there's a force, the charge is moving. So therefore, the field lines must be perpendicular to keep these charges from moving anywhere, because the assumption is it's electrostatic equilibrium. They wouldn't be equilibrium if they're moving. Component along the surface would cause the charge to move, then it would not be in equilibrium, and that's what we assume that it would be. So that fields must be perpendicular to the surface. They must be this way here, that way there, this way there. Well, actually, frankly, it looks like they've drawn these wrong. These should be, if these are negative charges, the field line should be pointing to the charges, like this. Okay? Okay, so that's why it made the description really hard to do, because if you had an excess charge of 3 minus, then the field lines would be pointing down. Not at an angle, that would make them move, they would be pointing this way. That keeps them from moving. Okay, property 4. Okay, on an irregularly shaped conductor, the charge accumulates at locations where the radius of curvature of the surface is smallest, that is, at sharp points. I already gave you illustrations of that. Let's see if they show a picture or something. Yeah, okay. Now, let's say you had excess charge. Here's your irregularly shaped object. It looks fairly regular to me, but it is. It's blunt on this end, sharp on this end. Okay? Now, let's say it has an excess of 4 minus. Okay? That's what that would indicate. Okay? Actually, those are supposed to be separate. I don't know why they do this. The excess charge moves to the surface. We've indicated that. The charges move apart until equilibrium is achieved. Okay? Well, guess what? On this part of the surface, there's more space for them to move apart. So they get further from each other. So you have less strength there. Over here, there's just not as much space for them to move. So they move as far as they can. They're on the surface, but you have relatively greater surface area, to include the whole thing here, with more charge on it, so you have accumulation on the points. Okay? Charges move apart until equilibrium is achieved. The amount of charge per unit area is greater, they said this backwards. The amount of charge per unit area should be greater at the sharp end, not the flat end. No, okay. If you notice in the book, the sentence that begins at the bottom of page 510 and continues at the top of page 511. As a result, there is less tendency for the charges to move apart along the surface here, that's the sharp end, and the amount of charge per unit area is greater than at the flat end. They forgot to put the than in here. So this sentence is wrong. That's totally wrong. This was supposed to have, and it's sort of taken out of context, but the sentence than at the flat end, not than is greater at the flat end. Sorry about that. The forces from the charges at the sharp end produce a larger resultant force away from the surface. Okay? So that's why they're accumulating there. And then if you give an opportunity for them to discharge, they're more likely to do it there than the other. Okay, because there's greater accumulation there. All right. With that correction, does this make sense? All right. Now, here's an experiment to verify the properties of charges. This is one performed by Michael Faraday. This is described on page 511, okay, beginning with the first full paragraph there. This Faraday's ice pail experiment concluded a charged object suspended inside a metal container causes a rearrangement of the charge on the container in such a manner that the sign of the charge on the inside of the surface of the container is opposite the sign of the charge on the suspended object. Boy, what a blah, blah, blah statement. Lots of words there. Okay, let's see if we can get a... Wow, that's all they say. Okay, sorry. They don't do a very good job of describing this. In the book, much better description. Okay? Basically a full page with lots of good illustration there. Okay? Is that Faraday's ice? Yeah, I think it is. That's the same as his ice pail experiment. Okay? Well worth a read and a go through. Do you want, without a slide, it's hard to describe, but you got your books, right? And you can go from there. If you have any questions about it, please hit. Very similar to what we did on an earlier description of another point. It's just not this particular one. Okay. Now this is another experiment, and this was a classic experiment. The Millikan oil drop experiment. Actually, when I first went back to grad school after I got out of the Navy, I'd done my undergraduate, got my commission, went in the Navy, served for 4 years, a little over 4 years. Came back and, applied for grad school, got accepted. And when I went back that January, there weren't a lot of classes that I could take. I needed to be a full load so I could use my GI Bill. And there weren't a whole lot of classes I could take. So I wound up taking one course that was called Advanced Physics Labs or something like that. Not my first and favorite course to take, but I needed 12 hours, so I wound up taking it. We did several pretty nifty experiments in there. One of them was the Millikan oil drop experiment. I'll try to give a basic idea of what's going on with that. Okay. What you have here is a little, like perfume sprayer, okay? Aerates, sends out just tiny little droplets, but it's got oil in it, not perfume. Okay, so tiny little droplets of oil went out. Okay? Now, what you have here, you set up an electric field. You put a plus charge on the top and a minus charge on the bottom. These are plates, and the top plate has a little pinhole in it. Through that pinhole, occasionally an oil drop, one of those little droplets that you sprayed above here, will fall. Okay? You know precisely the distance between those two plates, and because you set up this field between them, there are excess electrons down here, a deficit of electrons there, so basically you have some electrons that are moving. Some of those electrons will attach themselves to that oil drop that was falling through. Okay? So gravity is pulling it downward, but because this is electrically charged, negatively charged, this is your negative plate, the electrostatic force is pushing it upward. And literally you could stay, and they then set up this little telescope over here with an eyepiece, and you can watch, and they have light that is not directly across from this, but it's at an angle, so you can see the oil droplets easily. Okay? And you'll watch those oil drops. Some of them will come straight down at a very regular rate. Those are those that haven't picked up charge. Others, however, will pick up maybe one charge, and they will slow significantly. 2 charges will slow even more. 3, at some point, they actually start moving in the opposite direction. Gravity's pulling them downward, but the charge is pushing up. You know precisely the field strength here. You can measure that. And what you do, and the eyepiece there, I didn't say this, the eyepiece is horizontal lines across it. And those lines represent precisely, I don't remember, I'm guessing 1 centimeter. And you have several of them there. So you have a stopwatch in your hand, and when this oil drop comes down, you start the stopwatch, and when it reaches the bottom, you stop it. Okay? You can determine how fast that was coming. Those with no charge, you know how fast they're supposed to be going. Those with charges have been reduced a certain amount, and you can figure out from this experiment approximately how many charges on each drop. Okay? Because some of them will actually stop, some of them will move back up. You get a ratio of the speeds to the amount of charge on there. And it's a really nifty thing. So in this way, Millikan was able to measure the actual elementary charge, electron charge. Incredibly ingenious experiment to do so. He found every charge had an integral multiple of E, so therefore your charge was some integral multiple of that fundamental charge, okay, elementary charge E. That had been hypothesized before, this actually proved it. Okay. Moving on to 15.7, the Van de Graaff generator. Okay. Here's an illustration of it. And by the way, oh boy, the figure in the book, I wish they had this here for the Millikan oil drop experiment, on top of page 513, this shows an oil drop with the gravitational force pulling downward, the, I don't know why they use capital D, QE is a better one, to the force pushing upward. And, you know, it illustrates how you go about estimating and dealing with that. Okay. The Van de Graaff generator. Okay, what is that? Well, before I go any further, Robert J. Van de Graaff, okay, sounds like a good Dutch name to me, designed and built this electrostatic generator back in 1929. Now, have you seen somebody illustrate one of these before, demonstrate it? Okay, typically they'll ask some woman, doesn't have to be a woman, but it's more usually able to see it better. But if you have a guy with a lot of long hair, okay, he'll work just as well. I would be terrible to illustrate it because I don't have much hair and what I have is short. So you might be able to see it stand up a little bit, but not too much. But usually a woman, now their hair needs to have nothing on it. For instance, hairsprays and what are some of the palms or other things that people use on hair. If they got much of that on it, it's not going to do well. So really it needs to be clean, dry. If it's wet hair, that's not going to work either. The clean, dry hair will work the best, okay? If you got many oils on it, like if you haven't washed your hair several days, it won't work as well. So clean, dry hair will work better. And what they do, here's the electrostatic generator that he did. Okay, what you have here, you have something to pull off. This is ground. This pulls off excess electrons, okay? And because it's pulling off excess electrons, what you have here is the charges deposited on the belt at point A. What you have here, they don't show it here well, you have brushes. And the brushes is just like combing your hair, you know, with a comb, you're going to build up charges on the brush. And what this does is build up charges as it goes past the brush, and these are positive. You make sure this is fed by a positive charge. So you get positive charges on the belt, and the ground pulls off the opposite side, which are your electrons. The positive charges on this side, the electrons go there, the ground pulls off the negatives. So now you build up fairly substantial positive charges. Okay? Now, what you have is other brushes up here that brush the charges off onto the metal dome. Of course, there, the charge all goes to the exterior. Now, before you even start this, you have the woman up there, usually a woman or a guy with long hair, up on an insulated platform, touching the metal. Okay? So she or he transmits the charges too. You don't want them touching it after it's filled up charge, they're going to get shocked. You don't want them standing on the ground, they'll get shocked. They become the ground then. So what you want them standing up ungrounded, so they build up charge as well. When they do, the hair builds up charge. You don't feel anything except the hair starts standing up because the positive charges make the hair get as far apart from each other as possible. And if she's got really clean hair, really clean hair, dry hair, then you get a real display of hair standing up again. As soon as they turn it down, it flops right down because things discharge again. And they discharge the Vandergraaf generator as well. So the charge is transferred to the dome by means of the rotating belt. Eventually, an electrostatic discharge will take place. So you don't want to build this up ad infinitum, or else it's going to have arcing and sparking. You don't want that to happen. Things can get pretty bad at it. So the charge is deposited on the belt at A. The belt's going this way, so you deposit the charges here. They come off and go onto the metal dome. If they've got the handle on the dome. Now, there was a television show on one of the channels, I don't remember which one it was, History Channel or Learning Channel or one of those channels, and I can't remember the name of the show. It was not Mythbusters, but it was something like that. A reality show, people actually did things. And this show that they had, that I saw, actually a student saw it and wrote his paper on this. It was on making your own Vandergraaf generator. And it was pretty nifty. I mean, they did it from pretty cheap materials and did the thing, ran into problems, but but on the television show it showed how they did this, and they got it to work and stuff like this. So something like that, that would be an example of a demonstration or a YouTube video. It probably was about like a YouTube video, except it was actually a TV show, so I guess it was a little more sophisticated than YouTube video. Okay, but that's what a Vandergraaf generator is. All right, these are lots of short sections here at the end, or near the end. Electric flux and Gauss's law. Okay, we've talked about electric forces. We've talked about electric fields. Now we're talking about electric flux. What is that? It's a measure of how much the electric field vectors penetrate through a given surface. Now, the surface doesn't keep them from penetrating, so that's not what they're doing. It's saying how many field lines per surface area do you have? Okay? The field line penetrating area A perpendicular to the field, the product of EA, where E is the field, A is the area, the product of those two is the flux. The flux is given the symbol capital Phi. That's a Greek letter Phi. In general, for electric flux, we say Phi sub E. Phi sub E is equal to the electric field lines times A, the area, times the cosine of the angle in between. See, this is showing all perpendicular lines. They may not be. In fact, if you had a point source back here, these would be radial lines. Some of those lines would be going through perpendicular, but most of them won't. So what you do is E times A times the cosine of the angle in between. The angle in between, if that angle is close to 0, if it is 0, that's 1. Cosine of 0 is 1. If it's a little bit greater than 1, then this reduces them slightly. If it gets perpendicular it goes to 0 because cosine of 90 degrees or pi halves is 0. Okay, so this measures the components of the field passing through the area, perpendicular to the area. Okay. That figure is figure 1524 in your text. And same thing at the bottom of this page that starts the top of this page. The perpendicular area A is at an angle of theta with the field. When the area is constructed such that the closed surface is formed, use the convention that flux lines passing through the interior of the volume are negative and those passing out of the interior of the volume are positive. So if they're going into the area, those are negative field lines. Going passing out of the area, they're positive. Okay? The SI unit for flux is Newton meter squared per coulomb. Okay. Now let's see where that comes from. Here exactly. Field is measured in Newton per coulomb, and area is measured in meter squared. So it's Newton meter squared per coulomb. Cosine theta has no units with it at all. That just basically gives you a component of the vector. Okay? Now, let me go back to one thing they don't mention here. They may in the book, but I don't think they do. When you're talking about A, usually you don't think of A as being a vector, an area as being a vector, do you? Well, there is a convention. The vector component of the area is normal to the surface. So if this is a flat surface here, the normal component would be here. So that's the angle between the normal to the that plane, the angle between that and this. Again, if it's close to 0, you got 100%. Cosine of 0 is 1. If it's close to 90 degrees, then it's getting closer to 0. That would be the field lines going along the plane, not perpendicular to it. Okay. So that leads then to Gauss's law. All right. Welcome back. Right? Okay, we got half of our normal people here, almost. Megan's sick, right? Okay. And I think, didn't you say Courtney was sick? Did you? Okay. Sam is sick. Okay, now Sam is not really, I don't know, you might say so. He had to go to the emergency room this morning. He was in a lot of pain. And they figured out what it was, but all they could do was give him medicine to help the pain for today, so he's not able to drive. So that's why he couldn't be here today. Sounds like they're working on the problem. And then Courtney was, Brianna was in Huntsville, right? So looks like it's a small crowd today. So, well, I was just looking at that. These sections are going by very quickly, and we're almost at the end of the chapter. So I will. Now, today's lab, I don't have it run off. I don't think I do. Well, I think it's just a paper lab. Okay. Let's see. Yeah, your first lab was also a paper lab, right? Yeah. I think this one is too, because I just don't have the equipment to do any of this sort of sophisticated stuff. Let me see if I have it in here. I think I do. What's that again?
So if you finish the slides before 7:20, we're just going to go straight into the lab?
Yeah. And we have a real good chance of getting there. gave you all your first test too, right? Everybody got it? Okay. I knew I'd given it to you, but I want to make sure all of you were here to get it. Okay. Here we go. Fields and equipotentials. One. I only have 2 run off. I'll have to run off the rest of them. So one more and we'll have all of it. Again, I'm sorry that we're starting this with all paper labs, but in just a couple chapters, we're going to be doing more hands-on lab. We just don't have the equipment to do much of this. Some of it, I'll put it that way. All right. So that was electric flux. That's 15.8.1. And 15.8.2 in the new text, they break these down into a tertiary type thing. Here's Gauss's law. Now it's related to flux. Gauss's law states that the electric flux through any closed surface is equal to the net charge Q. Now before, we've been having Q as a little q. But when you have a large amount of this, usually you use capital Q here. So the net charge Q inside the surface divided by this quantity called epsilon naught. Now what is that epsilon naught? It's the permittivity of free space. And it has units of 8.8 or value of 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay? Now if you remember back, this is coulombs, right? Charges in coulombs. So if you divide this by something with this thing, the coulombs cancel out. Okay? Well, or 1 coulomb. This is 2 coulomb. One of these will cancel out. So you still have a coulomb. Because this is in the denominator, then you flip this over and you have a unit of Newton meter squared per coulomb. And a Newton meter squared per coulomb is exactly the unit for flux. So the units do work. Okay? So, this is how we define, well, this is Gauss's law. Now, by the way, another potential paper topic, who in the world is Gauss? Or, how did he come up with this law? What was the process he went through to get this? Or, you know, we have other possibilities there as well. Okay. The area in phi is an imaginary surface. It's called a Gaussian surface. It does not have to coincide with the surface of a physical object, like the surface of the conductor or the surface of the wire. Any actual surface is actually an imaginary surface, a Gaussian surface that you can place around the charge and then talk about the flux through that surface. Or it could actually be a true surface, but most of the time it is an imaginary. Because true surfaces are going to bleed off somewhere. You know, they're going to discharge something or something like that. So it's better to use imaginary surfaces. So here's the representation of this. Here's the electric field of a charged, thin, spherical shell. Okay? Electric field of a charged, thin, spherical shell. It's a spherical shell, meaning there is absolutely no charge, nothing on the inside because the shell is on the inside. There's nothing on the inside, so there can't be any charges there, so your flux on the inside is zero. Do a Gaussian surface, imaginary surface in there, no charge inside, so the flux is zero. Okay? Do a Gaussian surface on the outside, and now the net charge that's inside, that's whatever the charge on that surface is, and that gives you that's what you use for the Gauss's law calculation. So let's see, the calculation of the field outside the shell is identical to that of a point charge with that charge on it, however many pluses that is. Now, the electric field, the magnitude of the electric field, is Q over this thing. What in the world is that? 4 pi r squared. Does that ring a bell? Anyone know what 4 pi r squared is? It's the surface area of a sphere of radius r. Okay? So 4 pi r squared is the surface area of a sphere. So your magnitude of your field is the charge, either a point charge or the sum charge of that shell there, divided by the surface area. Now that's the surface area of your Gaussian surface, okay? Out here, that's the R here, okay? And then you have your epsilon naught down there. And again, epsilon naught was, the phi is Q inside the Gaussian surface over epsilon naught. And the, let's see, I need to go back maybe another slide or two. No, I don't guess we've gotten there yet. Okay. The electric field then, the magnitude of electric field would be the flux times the area. I think we did get there. Let's go back. Yeah. Okay. It's not showing here. They say, the product, here it is, here it was. The product of E times A is that flux. That's the field strength times the area is the flux. Now that's if the field lines are perpendicular. If you make your Gaussian surface centered around the charge, then the field is always perpendicular. So that's where you get EA is equal to phi. Divide both sides by A, the area of that sphere, Gaussian surface, is 4 pi r squared. So that's exactly where you get, and the phi, by the way, was the charge inside divided by epsilon naught. So your field would then be phi Q over epsilon naught divided by the surface area, which would be 4 pi r squared for that Gaussian sphere, Gaussian surface. What's more? Okay, now, I don't think we hit this before, but we're going to hit it right now. 1 over 4 pi epsilon naught, that is the same as Gauss's constant. 1 over 4 pi epsilon naught, which is the permittivity of free space, that gives you Gauss's constant. So there's your Gauss, almost Gauss's law again, not quite. This is in terms of, it is Gauss's law, exactly Gauss's law again. So the electric field inside the shell is 0. Why is that? Because the Gaussian surface in here encloses no charge. So the field in there is 0. Field out there, outside there would be just the same as if you had a single point charge of, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 12. If each one of those is static for a plus. Okay. So you see, we started with Gauss's law. Coulomb's law. We made our way around to Gauss's law, and that gets us right back to Coulomb's law again, with the understanding that Coulomb's constant is 1 over 4 pi epsilon. Okay. And I think, I'm still not used to this new book where these things occur. I think it's in the back of the book. Okay, yeah, there it is. If you go to the back inside cover of your text, okay, and you see Coulomb's constant, they show that as 1 over 4 pi epsilon naught. Ke, that was 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. You go down to epsilon naught, permittivity of free space, not permeability, but permittivity of free space, 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. So, constants are back there, everything is consistent. Okay. Okay. All right. Trying to find. Oh, and by the way, we just did example 15.7. I didn't realize that's what we were doing, but that electric field was basically doing example 15.7. Okay, or at least the first part of it. May not have done the whole part of it, but the first part was there. Okay, now we're looking at the Gaussian field, and this is example 15.8. Electric field of a non-conducting plane sheet of charge. That's not plane as in, oh, that's a plane sheet of charge. It's a level plane. Plane sheet of charge. And we're going to use a cylindrical Gaussian surface. You can make up any Gaussian surface you want. Choose one that fits the geometry of your question, okay, of your problem at hand. Okay, and since you got a plane sheet of charge in the shape of a plane, the best Gaussian surface would be a cylinder, because the fields are going to be going this way and that way, because it's a positive charge that goes that way and this way. Your cylinder here, things along here are not going to contribute anything perpendicular to the end. That will be, and that's the only area you're interested in. So there's your Gaussian surface. The lateral surfaces don't contribute anything because the field and the surface are in the same line, so they don't, your cosine theta is 0. So use a cylindrical Gaussian surface. The flux through the ends is EA, where A is the area of that circle at the end. There is no field through the curved part of the surface because that's in the same line of the EA. The normal lines are perpendicular to that, and cosine of that angle would be cosine 90, which is always 0, cosine pi s. The total charge is Q is equal to sigma A. Well, sigma is the surface charge density. Now, why they don't show that on the slide, I don't know. It's probably shown in the book. The surface charge density is what your charge per unit area, okay? Multiply that by the area of that surface, and you get the total charge. So, in this case, your E, if you remember, E is phi is equal to EA, so E is equal to phi over A. If your charge is sigma A, then the A's cancel out, and you're left with just sigma over 2 epsilon naught. Now, you might wonder why the 2. It seemed like before it was either 4 or 1. That's because you got 2 ends. You got an area up and an area down, and you got charge going through both of them, or field going through both of them. So that's what introduces the 2 for you there. Note the field is uniform, and in effect, some of it's going up and some of it's going down. see in the book if they do a little bit better representation of that. EA is equal to your that is your phi. That's Q on the inside divided by epsilon naught. And Q on the inside is sigma A. So you have sigma A over, that's your Q on the inside, over 2A naught. Well, they don't do a good job on that either. Okay, but if you read through that and follow along, they off on the side they give you all the reasons that those are in place. But basically, you have two ends, and that's where the 2 comes from. The total area is 2 times the single area, and when you divide by that, you wind up with the 2 down there. A's cancel out. All right. Now, building on that, your E is sigma over 2 epsilon naught. Building on that, what if we had a situation like this? Electric field on a non-conducting plate sheet of charge, this is continuous. The field must be perpendicular to the sheet. Obviously, you couldn't have a component anything but perpendicular because then the charges would be moving. They're not moving. The field is directed either toward or away from the sheet. You have field going in both directions. And the flux phi is EA0, where A0 is this area here, or here, or here. All those areas are the same. But the Q is epsilon times A naught. Okay? So, there's your Gaussian surface, that cylinder, with the ends being A naught in area. Your flux then is EA0 on both top and bottom. And really nothing new is shown in this that I can tell. Now, what if that was a negative plate, non-conducting plane or sheet of charge, and it was charged negatively, then your field lines are going in. So the same Gaussian surface would work, only your field is going in, not out. Okay. This is good for Z greater than 0, Z being the distance from the plate. Don't do it right at 0, but some greater distance. All right. Now, this is the first place that we introduce a parallel plate capacitor. In a later chapter, we're going to do lots of stuff with capacitance. Here we're just introducing the thing because we basically already talked about both parts of it. Okay? A parallel plate capacitor is a device that consists of 2 plates, one is positive and one negative. Okay? Now, usually these are conducting plates. The ones we were talking about before were non-conducting plates, but I don't think it's a huge difference here. In the parallel plate capacitor, we don't let the charge leave the plate, so it's just like they were non-conducting. They just build up on the plates. Now, before we had, when you didn't have this, it was E over epsilon, or E over sigma, 2 epsilon naught. But this one would have been the same thing, so when you have both of them there, you just get sigma over epsilon naught. Your E on the outside is 0, okay? The reason for that is all the field is pointed toward the other plate, okay? So the total electric field between the plates is sigma over epsilon naught. The field outside the plates is 0. All the field is concentrated there. And you talk about a concentrated field, all these lines are very close to perpendicular. Only when you get the very outer regions, you get a little bit of bending of them here. But if the dimension of the plate is significantly larger than the distance in between, you have basically a uniform field line. Okay. And it would have a magnitude sigma over epsilon naught. Now that's all we're going to talk about a parallel plate capacitor at this point. Okay? And that basically ends the chapter 2. The next topic, I'm sorry I said chapters, topics now. The next topic is going to pick up on this electrical energy and the capacitance we introduced right there. We didn't define what capacitance was, but we did introduce you to what a capacitor was. Okay? So that is, I think, the last slide. And what I need to do is, we're just basically 40 minutes into the class. Okay? So what I think I'm going to do now, let's wait and do the lab the last 2 hours. So that will be 7 to 9, right?
Yeah, lab starts at a couple minutes.
It's what? Oh, no, I'm sorry. It's 7 now. Okay, I'm sorry. I looked at my clock wrong. Okay, it's what?
7:08.
Okay, this is the perfect time to start the lab. So let's take our little break now, and let me go run off the additional copy I need, because I think I do need one. Okay, and what I'll do now, not only run off the lab, I'll get y'all started on the lab, then I'll come back and run off, while y'all are working on the lab, I will do the, go run off the test for this chapter. Yeah, the second test. I already gave you the first one, right? Okay.
Monday, so I'm guessing Monday you're going to give us the second test?
What's that?
When are you going to give us the second test?
Today, tonight. But I'm going to run it. I don't have it run off right now.
Oh, okay.
I'm going to run it off while y'all are working on the lab. Okay. So, let's see. The two of you want to go on and start on this? Okay. Y'all can all work together. Actually, let me go on and run it off so I can explain it when all of you are here. Okay? I mean, you got it completely in front of you. And this is, in one sense, a pitiful little lab. Okay? Okay. So let me run this off. I'm going to put this on pause. I'll repeat all that again. Okay. Sorry about this. Y'all can get started. Your second lab consists mostly of a paper lab. The handout says Experiment 24, Fields and Equipotentials. Read the top of page 291 and the bottom of 291. The middle part you don't need to read. I have the X through that. Then read the first part of 292 down to the X on the B. You also have some diagrams there I think you may find useful later. Then start answering the questions on the following pages. 287, there's 2 questions there, but they have 2 parts each. If I don't get an answer to both parts, you're not going to get credit for both. So that's up to 4 points there. 288, I should have left that page out altogether. Page 297, there's question 2. Don't do question 1, but do question 2. Again, there's 2 parts, so that's up to 6 points worth. Top of page 298, question 3 has 2 parts, an A or B part. So that's 2 more points. That's up to 8 questions, 8 points, I think. Question 4. Question 4 has 2 parts, A and B. So you draw the field lines for that one, and that will be, and by the way, folks, just from my experience of before, I would definitely make these drawings with pencil so you can erase if you mess it up and not say, oh, I need another one, I messed these up, you know. So I would definitely use pencil on the drawings. Okay, so there's 2 more. What was that up to? 12, I think, or more. Let me go back and count. Page 287, 24, 288, 6, 297, 8, 298, 10, 12, and then on the page that's not numbered, there's 6 questions, 12 and 6 is, that comes up to 18, doesn't it? Go through and count again. 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18. Scratch what I said before, 18. That leaves just 7 or more. 7 or more questions from the, and you can get all 7 of those on conceptual if you want to. If you want to substitute some conceptual, you can, but it's 7 or more questions of the even-numbered conceptual questions on page 520 and 521.
Okay, so what I'm looking at, I have 1 through 17. I'm in the older edition, and it's 8 problems that you can use that's even through 17.
Okay. Let's see what you're saying.
1 through 17 of the conceptual questions.
Okay, except I said do the even numbers, right? Because the odds are in the back. So I don't want you doing one that the answers are in the back of the book. And make sure they're, your conceptual questions, see your odds are back here. So if you do these, the even number, you have 8, and you do any 7 or more.
I
Now,
thought don't do one of these.
huh?
I thought, okay, since it's 8 even, can we not do all 8?
Okay. What I said is 7 or more of the even conceptual questions. That means you can do all 8 if you want to, or at least 7. Now, why would you want to do all 8? In case you miss one of the others, you get, I mean, I'll count your 7 best answers.
Oh.
That's why I said or more. Now, you can't get more than 25 points for the lab, but you can get, if you miss 1, you can still get, if you do 8, you can still get 25 points. You won't have 24. Okay. So that's why I said do 7 or more of the even numbered conceptual questions on pages 520 and 521. Okay. Any questions right off the top? Okay, what I'm going to do is go down and run off the test next. So I'm going to put this on pause. Okay, I've just handed out the test for topic 15. It's a 1-page, 10-question, I think it is, isn't it? Yeah, 10-question test. So if you aren't here today, get it from me when you can. Okay. I'm going to go and shut down the PowerPoint, because I don't think we'll be needing that anymore. And I will pause this.